computer. And then I want to share that. And hopefully everybody can see my notes. And we're going to start. We're going to be today talking about the most important encryption process called RSA. We're going to start on about encryption, and then what the other part of RSA is based on Horst Feistel. So we're going to start about that first, and we'll move on to RSA. Whoops, wrong way. Okay, we've done the abstract several times. We're in chapter 14. So last week, I finished up with the Hamming error code. And if anybody saw the lectures, I added several examples at the end of the work that I had done last time. And this was the example that was used in Shannon's 1948 information theory paper. And although he'd only proved an existence proof for error code, not a constructive one, he did use Hamming's 7.4 as an example, showing that indeed you could do error correcting codes. Okay, so this week I'm going to do a short background, and we're going to maybe not so short, and we're going to move on to Horst Feistel and his work, which culminated in the data encryption standard in the 1970s, and it was used in stream ciphers and block ciphers, and is actually now sort of a part of the RSA public key crypto system. The reason that it's part of it is that RSA is very slow compared to block ciphers. And so the keys for block ciphers are sent back and forth using the RSA, and then the RSA is used for the actual encryption. So the science of information is also the science of secrets. Actually, it was the sort of the first kind of coding that was ever done. And the so far I've only focused on communication and information theory, but it can also be used to defend information from errors in transmission. And those were Shannon's first and second fundamental theorems. But they have another purpose, to conceal information, to protect the privacy of messages. So that's the concern of the field called cryptography, and cryptography encompasses all of those situations. And in fact, it is something that we rely on usually without even knowing about it. Passwords, which I've already discussed in previous lectures, are the simplest example. So the whole point of a password is that the right people should know it and the outsiders should not. In effect, a password is like a key on a door. The only people who possess the key can open the lock and be granted access. The strength of that lock determines how many possible keys there are.
Okay.
Miguel, yes?
All right, you're back again. We lost you for a while.
Yeah, I got a unstable internet message. So, okay. So the strength of a lock is determined by how many possible keys there are. And this, in turn, is measured by the entropy of the password. If the entropy is, Lee, would you please, or Bob, would you please mute everybody except me? If the entropy is low, there's relatively few possible passwords, so an adversary would be pretty easy to guess the right one in a relatively short time. A password with high entropy is chosen from a gigantic set or huge set of possibilities, and hence I'm confident that the adversary won't be able to guess the right one. The exact same ideas apply actually to a physical key that operates a mechanical lock. So this is the way a tumbler lock works. You have a cylinder in the middle of it, and you have a bunch of holes going down, and this is an old design. It was actually the ancient Egyptians who seems to be the earliest creators of it, but the principles on which they work are essentially information principles, just like a computer password. So the key is a piece of metal machined into a particular shape. Those grooves along the side, they have these high and low places along the top edge of the key. Okay, so there are grooves in the, the key without a proper pattern won't fit the lock. Why? These pins are pushed down, and there's two pieces to it. There's a lower portion and an upper portion. When they're pushed into the improper lengths, it won't turn because it locks up against the top pieces. However, if you have the proper key, then all of the upper pieces are right at the top edge of the cylinder, and you can use only these pins to turn it. And that's the way the key locks and unlocks. Is that fairly clear about how it works? Has anybody got any questions about how a tumbler pin lock with key unlocked and locked shows? Any questions? Okay. So the outer, as I said, the outer casing with a cylinder is called the plug. So the cylinder here is a plug. Turning the plug would unlock the door, but it usually can't. There's a series of these fibers and holes in this region, and these are fiber and these are fiber, and they're of different lengths, if you notice. So this has one length, this has a longer one, this one's shorter one, etc. And these have corresponding complementary so that the overall length is the same. Now, if you put in a key that doesn't fit, then when they are pushed into up and down into positions, they don't match with the edge of the plug. If you do have the proper structure in the key, then they all exactly line up with the edge of the plug. And so when you turn the key, the plug will turn and you can open the lock. Okay? So again, this is all how it works. Is this all clear? Any questions?
Oh, fine.
Okay. So since the driver and tumbler pins are separate pieces, the plug can now rotate, as I said, and the outside lock, anyone can see what the pattern of grooves is needed. So you need to not let the key be in the hands of somebody else. Okay, so the potential intruder cannot know the key shape, unless they've gotten a copy of the key. It is the hidden information, the secret password, which makes the lock secure. How many bits of password information are there in a door key? Well, we can make an estimate. Let's say the lock has 6 tumbler pins. Each tumbler could have a range of possible lengths, anywhere from 5 and 10 millimeters, let's say. This is like the analog of information in an electrical voltage. So analog variables, and of course a mechanical lock is an analog one. You can wiggle them around a little bit, and 2 keys with the same lock will also have microscopic differences, and the lock still has to be able to work. So that means that there has to be a finite number of really distinct tumbler pin lengths. And just playing with it, my guess is about 8. So the possibility means that the entropy of log 2 of 8, or about 3 bits for each pin. So for a 6-pin lock system, that's 18 bits of entropy, which is not too bad. The 4-digit code that used to unlock my old phone, now it uses 6, has 13 bits of entropy. So if you try all possible keys on locked doors, it would be highly impractical. An intruder would have to bring along 250,000 possible different keys, and it would take months to try them all. So that's not possible. That's the way a physical key works. In the subject of cryptography, we want to go much beyond locking our front doors. Cryptography is the secret of communication, and it is tremendously important. The fates of wars and nations have depended upon it. And if you've come through the lectures so far, you probably shouldn't be too unsurprised to learn that Claude Shannon was also interested in cryptography. In fact, he worked on cryptography during Second World War, and it was that work that was an inspiration for information theory after the war. I'll talk about Shannon's wartime work in a few minutes. Shannon rediscovered a old principle, Kirchhoff's principle, and gave it a especially pithy form that's now called Shannon's maxim. The enemy knows the system. That's the quote, which I missed the quotes on it. In Shannon's terms, a cryptographic system is a whole set of possible codes that Alice and Bob might use. Eve does not know which code they're using at the moment, but we must assume she knows that the possibilities are. So the information that Eve does not have, the choice of code within the system, is called the key to the code, just like a key to a door lock. And if the entropy of the key is high enough, Eve would have a hard time guessing it. So in 1943, during World War II, Claude Shannon and Alan Turing were called on to evaluate the security of an encrypted telephone link that allowed Franklin Roosevelt and Winston Churchill to confer in secret across the Atlantic Ocean. That system was codenamed Sig Sally, and it was the first ever designed to protect the privacy of that kind of electronic communication. There's actually a display of Sig Sally. Actually, this is about 1/3 of the total equipment that was used. It was enormous at the time. And if you are ever in Washington, D.C., you can go to the National Cryptologic Museum outside of Washington, and this is a display on the museum. So it was an absolutely amazing technological achievement in its day. Here's how it worked. First, Sig Sally was the very first telephone system to convert analog voice signals into digital information. So this was when the idea of pulse code modulation, which we've talked about previously, was first understood and created. So the digital signal amounted to a highly compressed version of the original voice data. That was important for two reasons. First, it required less bandwidth to transmit the compressed data. Secondly, and more importantly, the compressed voice data had much less redundancy than the original voice data. So we've talked about Huffman codes, and you can reduce the amount of redundancy in that. And that, of course, since cryptanalysis relies on that redundancy, my connection was again unstable, so I'll start again. The cryptanalysis relies on that redundancy, so compressing it reduces that amount, the eavesdropper's job harder. But the real secrecy of Sig Sally came from the cryptographic key. The key was a pair of identical phonograph records. Each one of those records, they were identical. Each pair of those, one was sent to London and the other was to Washington, D.C. And each record contained random electronic noise, the exact same noise on each, obviously. Before the Sig-Sally voice transmit data was transmitted, it was added to the random noise from the record. At the other end, the same noise was subtracted from the received signal, yielding the original. That in turn was decompressed and turned into recognizable, understandable telephone voice. So the two key records, thousands of miles apart, had to be synchronized to within roughly a couple of milliseconds so that the same noise was added and subtracted. And also each record contained only, because of the limits of the size of a record, they could only have about 12 minutes of conversation. So a second pair of records also had to be set up to start on different turntables in case the call went longer. So the two systems, the analysis of the system from the US side was by Shannon, and the analysis by the the British side was Alan Turing. And Shannon and Turing concluded that Sig-Sally was indeed secure. Here's his analysis in a nutshell. The enemy can intercept only what is actually transmitted, the combined signal, voice data plus random noise. That's the ciphertext. Now, the enemy knows nothing about the contents of the noise record, the key, and that's critically important. Therefore, any voice transmissions whatsoever is consistent with what the enemy learns. The phone conversation might contain military plans, chit-chats about the weather, baseball result, anything. For any plain text voice data, there exists a possible key, a possible pair of noise records. And that would make it look like the received ciphertext signal would just be noise. Therefore, eavesdropping the enemy, the eavesdropping enemy learns nothing, and the system is secure. Is the argument clear for people? Is there any questions about it? Okay. Indeed, during the war, German technicians at listening posts recorded many of the Sig-Sally transmissions, but they were not able to decode any of them. In fact, they didn't even know they were encrypted telephone communications. So how can it be that this cryptographic system defeats every possible type of cryptanalysis? According to Shannon's description, the secrecy comes from the gap between the secret information and the information available to the enemy. So the gap starts out with the entropy of the key. H of K, K being the key, H being the entropy. Because of the entropy of the redundancy in the plain text message, so this is the entropy of the message D, the gap narrows at time, over time, when you normally hear the encrypted messages. Because of the redundancy in it, the gap keeps narrowing over time. Unfortunately, I apologize. The mowers are going and the dog hates it. So I'm going to close the door. Excuse me, I'll be right back.
Did anybody sort out whether the noise was actual conversation or was it more like just random electronic signal?
I think it was just random noise, and it probably digitized.
Well, then how did the Germans? I mean, if when they read it, how did
Okay.
they couldn't decrypt it? But we had a question while you were away.
Okay.
The noise that was introduced into the signal, was that like a random noise or was that actually some kind of conversation?
No, that was complete random noise.
Random noise. Okay, so the Germans couldn't determine whether there was actually a conversation going on.
No, all they heard was noise.
Noise. All they got was noise. So they may have recorded noise, but they couldn't do anything with it.
Right.
Got it. Thank you.
Because they didn't have the key. They didn't have the records that had the noise that had to be subtracted.
Wouldn't that be a pseudo-random? It appears to be random, but it actually has a
No, this
sequence to it.
wasn't digital random noise. This was real electronic random noise. So, and
No, but it had to be digitized before it was sent over.
no. Remember, this was an analog system.
Oh, I
So-
thought you said that they sent it as pulses.
Yeah, but PCM is still an analog system. You have an electrical system which can be either high or low, but that's a current. And the current is either up or down, or up, down, 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 up, down, etc. So, but it's all an analog signal, even though it's PCM. It's a way of taking analog signals, digitizing them, and putting them in an analog system. You've got a current that's going up and down over time. In fact, now the way it's done is that you only take, you don't actually look for the ups and downs. You don't actually make them into signals that go all the way up to 1 for a while and then down to 0 and up to 1, etc. What they do is they go with some kind of a complex analog signal that, and you determine the locations in time of the places where the zeros occur. And once you know that 1 is up, the next time it goes to a 0, it goes to a down. The next time it goes up to a 0, it's going back up to a 1. So you keep knowing the length of time between the times it goes between 0. And you can infer, because the length of time of every bit is the same, how many bits were up versus how many bits were down, etc. And you keep doing it that way. You don't actually even use digitized signal. They're still analog, but you only look for the length of time between zeros, and knowing which one starts it at positive or negative, whichever it is, you know whether it's going to be a 0 or a 1, and then every time after that it just switches back and forth. And by the amount of time between the zeros, you can count the number of bits up versus the number of bits down. Got it?
Yeah, but I would consider that digital signal.
It is a digital signal, but it's using an analog transmission channel.
The question was the noise added to the signal after it was digitized in an analog form?
Yes, it was. It's an analog system all the way, and the noise was analog as well.
Okay, so you added the analog noise to the pulsed signal.
Right.
So it just looked like analog noise when it came out the other end.
Right.
Okay.
Okay. So, I mean, the original systems were much more, the PCMs were actually trying to make bits. You know, they push the current to 1, hold it for a period of time, drop it down to 0, hold it for a period of time, go up. It was a much more frequency dependent, you know, you had to use many more frequencies in the analog signal in order to send them in PCM the way it was originally designed. But we've reduced the amount of frequency needed by using the signal system that I just talked about, where you only look for the locations of the 0 in the current coming along, and then you just count the amount of time, and you start the original one, figure out whether it's going up or down, and then you can figure out you can infer all of the bits up and down from the length of time between the zeros. So much less bandwidth is needed today than it was used at the original system, which was designed in World War II, you know, and that was the first time it was done. So is all of that clear? Any other questions?
Thank you. No.
Okay. So the way in which the adversary can learn what the key is you have the entropy of the key, and because of the redundancy of the message text D, eventually they can use that redundancy to lower the understanding of what the entropy of the key is until the gap between those two is 0, and at least in principle, the enemy can read the message. Now, the amount of time it takes to do that is called the unicity distance, and it is the entropy of the key divided by the entropy of the messages. So the L equals the entropy of the key divided by D. Okay. So it tells us how long a message needs to be in order for the code to be broken. Now, notice the assumption in that analysis. The secret key has a fixed entropy, H of K. Therefore, the secrecy gap starts out at a fixed size and gets narrower over time. That's how the enemy catches up. But in Sig Sally, the key information the key of the information and the entropy of the key grows along with the message, because every time they ended one record, they would add a new pair of records on each end, knowing, you know, the order in which they were to be used was record 1, record 2, record 3, up to however many records there were overall. I don't know how many they were, but in practical terms, this means that the secrecy gap grows wider and wider, because no matter how much entropy of the message is that they receive, the entropy of the key keeps getting longer and longer and longer. So the unicity distance, the amount of time it takes for the enemy to decode, goes to infinity. It's the absolutely most wonderful design for cryptography.
If noise is added artificially to defeat the ability of the enemy to understand the message, what about natural noise that would occur?
Well, you know, you have to have very high quality messages sent. You can't have much noise in the system. This depends upon there being very low noise, and the way the system in the cables between the United States and Britain they were very high quality. So this wasn't much of a problem. Okay, any other questions? My internet is unstable again, I apologize. This general approach to cryptography was known in Shannon's time as a one-time pad. So you can picture Alice and Bob, each with an identical pad of secret keys, and the pad is infinitely long. So on every time you want to send a message, a new key on each page in the pad is used. So as the message is sent, you use the keys on the pad until you run out of keys on a pad, tear it off, and destroy it. So you use then for any more messages, you keep using new symbols. So the keys are continuously different. They're infinite in length. And this is the design of a one-time pad, an infinitely long pad. And Shannon showed that the one-time pad is perfectly secure. It's code that can't be broken by cryptanalysis. And since Sig Sally was that type of a system, it was secure as well. Not only in principle, but actually in practice. So let's start talking about cryptography in digital communications. We'll describe a binary version of the one-time pad. Alice's plain text is a string of bits. They might be teletype codes or digitized sound, whatever, it doesn't really matter. They're just bits. The key, so that's the plain text. The ciphertext is created by using the key. The key is a second randomly generated string of bits, secret, but shared by Alice and Bob. To generate the ciphertext, Alice combines the plain text with the key bits using the XOR function, which we looked at last week. And if you recall from our discussion of Boolean logic, the bit XOR plus sub 2, mod 2, truth table says that 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. So that's the way in which you create the ciphertext. You take the plain text bits and you use the secret key bits, and each one that goes along, you XOR between the two. Since the key could be anything, any particular ciphertext string, which Eve might intercept, is consistent with every possible plaintext message of the same length. At this, and at his end, Bob receives the ciphertext, and in order to recover the plaintext, he just applies the XOR operation again using the key string he also has. Again, in order for this to work, you have to have very high quality of messages sent. And
Hey, Bob, you drop out from time to time. Why
yes,
don't
I'm trying to stop when I see it come up, and I'll start it over again. But
okay. The other option is to just have Lee Gale raise her hand every time we can't hear you. You know, then that's the second way of doing it.
Yeah, okay.
You mean my physical hand or the
No, your physical hand. Just put your
okay.
hand up, and he can have your.
Yeah, if you just hit your space bar opening to say something, you don't actually have to say something, but your face shows up on the screen, so I know it's you. And if you do that, I'll know that I'm receiving bad. I've got an unstable internet, and I'll stop and start again. So you've got the ciphertext that Alice has created by taking whatever message she's sending, and she's taking a set of key texts, key bits, which each of those is secret, but Bob knows exactly the same ones are coming to him. And so she XORs her bits with the key bits. And somebody, I think Fred, would you please mute yourself? At his end, Bob receives the ciphertext, and to recover the plaintext, he just XORs again using the key string, and out pops the plaintext. So using the XOR is the key or is the mechanism that yields the appropriate encryption and decryption. It's a very simple, but again, assuming that they use the same key string, and as they have each message, they destroy the keys then and start the next one on the next message. So it's a binary version of the same one-time pad, and it makes it absolutely undecipherable. Now, the problem comes if Alice and Bob try to reuse the key. The system would no longer be perfectly secure. And this is not just a theoretical issue. It was a basis of one of the most remarkable episodes in the whole history of cryptanalysis. During the 1930s and 40s, the NKVD, the Soviet Secret Intelligence Service, communicated with its stations in Soviet embassies around the world using ordinary commercial cable messages. Now, those messages were extremely sensitive. Fred, please mute yourself. Bob, would you please make sure everybody but me is muted? Thank you. So the Soviets were sending these using ordinary commercial cables, and the messages were very sensitive because they contained details about Soviet spies in the US, Europe, and elsewhere. Now, the Soviets adopted a one-time pad system for those messages. Or rather, I should say, that's what they did in theory. Now, for reasons that are not entirely clear, laziness, carelessness, for some reason, the code key sheets were sometimes used in many different pads. Now, these pads might be issued to different stations. So one might be to Turkey, another to Canada, but the overall result was that sometimes the same key would be used more than once. So the encrypted cables were intercepted and recorded by the US, Great Britain, and their allies. For a long time, nobody could read them. But in the 1940s, the US Signal Intelligence System at Arlington began to realize that the same key pages were being reused in different locations. So they started a project to exploit this mistake to decrypt some of the cables that had been intercepted. This was called the Venona project. Now, even though the Soviets had tipped off to the project that the new codes had been understood by 1945, the US and our allies kept using Venona for decades. Ultimately, about 3,000 messages were decrypted, many of them decades after they were sent. Now that might seem pointless, because, I mean, why do you work so hard to unlock secrets from 30 years ago? Well, remember, many of those messages contain clues to the identities of Soviet spies. And even into the 1970s, 30 years later, the Cold War was still going between the Soviet Union and the United States. Today, it's long gone, but at that time, understanding who were the Soviet spies in the US or Europe or anywhere else was really pretty important. So now that it's long gone, you can freely read the decrypted Venona messages online, and they're just a really interesting window into the secret side of history. Okay, so today's cryptography uses a different procedure. Most modern cryptographic systems, the ones used by computers, phones, and everything else, uses a completely different approach. They rely on what computer scientists call computational complexity. Now, that's a subject that studies how difficult different mathematical problems are. Any calculation is made up of a series of basic steps. Some require many more steps than others. Some require so many steps that no imaginable computer could finish them in a million years. Those problems are solvable in principle, but not in actual practice. So let me give you an example from arithmetic. You probably remember that a prime number is a number which is a whole number and divisible only by itself and 1. So an example would be 17. There's no factors of 17. So prime numbers as big as, you can of course find prime numbers as big as you like. So whole numbers, which are not prime, are called composite numbers. Most modern cryptographic systems, ones used by remotes, computers, phones, everything, are based on this. I think I just repeated part of what I said, so I apologize. Yes, it is. Why isn't? Okay, how about this one? All right. Any number, prime or composite, can be written as a product of one or more primes. For example, 35 is 5 times 7. 36 is 2 times 2 times 3 times 3. So 2 squared times 3 squared. And this is the first 100 numbers. And you can see that every number that is prime, 2, 3, 5, 7, 11, 13, 17, 13, 17, 19, etc. All of those, there's nothing else that you can break them into. But everything else can be written as 24 is 3 times 2 times 2 times 2, or 3 times 2 to the 3rd power. So 64 is 2 to the 6th. So all of these numbers can be created into these different factors. So suppose somebody gives you 2 prime numbers. For example, we'll say 2,273 and 4,057. So your job is to multiply them together. That's pretty easy. Even with a pencil and paper, you can probably do it in a minute or maybe 2 at most. The answer is 9,221,561. So I did an experiment on my computer. I wrote a program to find out how long it takes my computer to do that multiplication. Frankly, it's actually quite hard to measure the time, a time that short. I found that it was less than 4 nanoseconds. Modern computers are very fast. That's a truly tiny interval of time. 4 nanoseconds, moving at the speed of light. It shouldn't be light, sorry. If you had some object moving at the speed of light, a photon, during 4 nanoseconds, it goes about a yard, 3 feet. So it's not very much at all. Suppose you were given the opposite problem. You were given the number. Sorry.
Did you see my hand up? I don't.
Yeah.
Did that work? Yeah. Okay.
Right. Okay. So suppose you're given the opposite problem. You have the number, the 9,221,561, and told that this is the product of 2 primes. Find them. That's called the factoring problem, factoring a number. And it uses a lot more work. Essentially, you try dividing the number by virtually every possible factor and check the time it takes to find out whether or not the division has a remainder or not. And by hand, you'd be lucky to finish in a whole day. My computer managed to factor that number in about 17,500 nanoseconds, as opposed to the multiplication, which took 4 nanoseconds. So essentially a little over 4,000 times as much time as multiplying it. So even though computers are amazingly fast, and it's only a few millionths of a second, but it's many, many thousands of times longer than the multiplication. So I tried the same experiment again with 2 bigger primes, 9,747 and 1,289,557. Their product, 1,251,833,589,079 has 13 digits. Now, it again took about 4 nanoseconds to multiply those, but factoring those with that big number and working backwards took 544,000 nanoseconds. Just, 100,000 times longer than multiplying them. So the basis of cryptography today is factoring large products of prime numbers. Factoring is just plain harder than multiplication, bigger, and the bigger the numbers involved, the more dramatic the difference. Suppose my 2 prime numbers had 70 digits instead of 7. Their products would be about 140 digits. On my computer, multiplying those numbers might take perhaps a few hundred nanoseconds. and it would still be fast, less than a millionth of a second. But factoring 140th number, 140 digit number, would take my computer not minutes or hours or weeks, but probably longer than the lifetime of the universe. So what's the record? In 2009, using an efficient program, much more efficient than mine, a 232 digit number was factored. Now, it took hundreds of computers working together for about 2 years to factor that 232 digit. So they had 100 computers working together for 2 years in order to be able to factor that 232 digit number. That was multiplication of 2 primes. So this is the basis today of encryption. This is what computer scientists call a trapdoor function. If you know the 2 primes inputs, you can find their output very easily, their product. Given the input of the output is also possible in principle to compute the input. But from the point of view of information theory, the input and output contains exactly the same amount of entropy. However, the trapdoor function going backwards from the output to input is vastly more difficult. It requires much, much more effort, much more time. It might, for all practical purposes, be impossible. So once you pass through the trapdoor in one direction, it's really, really hard to go back. It might be barely possible that there's some clever, quick method for factoring numbers that no one has yet discovered and might happen in the future. And in theory, quantum computers might be able to do it faster, but the biggest number that a quantum computer has ever been able to factor is 15, 1, 5, 3 times 5. So they've got a long way to go until quantum computers are actually usable. This is a very secure basis of encryption, and it's called the RSA method of encryption.
Bob, could I just add something for a minute?
Sure.
You've probably emphasized or will emphasize this, but just in case, I want to mention that the big feature of the RSA method is that you've solved what's called the key distribution problem. In all the previous encryption methods, the receiver of an encrypted message must have the key. So the sender somehow or other must deliver the key to the receiver. The RSA method avoids that problem.
Right. It's a public key method, which we're going to talk about later. You're absolutely right. Thank you.
I wanted to ask you, each of these numbers, these huge numbers, represent what? A letter? Each number represents a letter to be decrypted or to be decoded
Well, in practice, because this is such a, even having the codes distributed and known is still a difficult process compared to what are called stream ciphers, I think, or block ciphers. The way in which encryption is actually used is that the keys that are sent back and forth to a receiver, the ones that are used to encode the keys are encrypted using the RSA method, sent to the receiver. The receiver uses the RSA method to decrypt a key. Then the message was sent using the key in a regular, essentially a one pad key. And so it's the use of RSA to use the keys back and forth between a sender and a receiver on a one pad key and that's used for a much larger block of bits. So it's a two-part process. You encode something using a one pad key, but that needs to be sent secretly to the receiver. So that key is encoded using the RSA method, sent to the receiver. The receiver receives the key encoded, decodes it using the RSA method. Then the text, the ciphertext, which has been encoded using that key, is sent. That text is, or bits are decoded, and the process repeats. So it's a multiple step process. Was I clear in explaining how it works? Lee Gale? You're thinking hard. Oh, you can't hear me. Sorry.
Yeah, we lost you at that process repeats.
Okay, sorry. So the process is you have a one pad key. That key you need to transmit to a receiver. So you encode the key using the RSA method, transmit it to the receiver. The receiver uses the RSA method to decrypt the key. The original message is encrypted using the one pad key, sent to the receiver. The receiver now knows the key, decodes the block of bits, and you have the message sent, and the process is repeated. So the next random key for the next block is encoded using the RSA method, sent again to the receiver decodes it. The block of bits that have been encoded using that key is sent. Those blocks are decoded using the one pad key, and then the process just keeps repeating over and over and over again. Is that clear?
I think it's clear. So what you're saying is they keep changing the key. The
Right,
key is every pad. It's from the old-fashioned, paper pads. They use that word pad, but in other words, it's a periodic changing of the key.
Right, and they use the RSA method to transmit the new key. that is randomly created each time a new block of bits is sent.
So that's how they get the key from one side to the other. So why can't the enemy intercept the key?
Because it uses the RSA method to encrypt the key. So they'd have to be able to figure out what the long, big two numbers are that are used in the RSA method.
I think I understand, yeah.
Okay, so the key is sent encrypted using the RSA method.
So the receiving end previously has the RSA
Right, we're going to get into we're going to get into the way the RSA method works, and it's an asymmetric, and you have parts that are secret and parts that can be public, and using that on both sides, we'll get into that in much more detail as we go along. But yeah, so it's a two-part process. The first is to use a regular, ordinary one-pad key, but make that secret by using the RSA encryption, sent it to the receiver who decrypts the key. Then you send the ciphertext in the key, and that ciphertext is decoded by the receiver because it had just previously received the key using the RSA method. Mm-hmm. So it's the fact that the RSA method is so difficult and so time consuming that you can't do the whole text using the RSA method. You have to use a one pad key, which as long as you keep changing it, forever, it's the unicity length, the time it takes to decode, still goes to infinity, so it can't be broken, but you have to have the keys match with each other, and doing that, on the fly is you use the key using the RSA method in order to send the key back and forth, and you keep changing the key, send it, change it, send it, etc. And every time you sent it, you use the RSA method to encrypt the key and decrypt it on the other side. Okay, all clear? Any other questions? Okay, we've moved on to Horst Feistel. Feistel, born 1915 and died in 1990. Okay, Feistel was born in 1915 and died in 1990. He was born in Berlin, Germany, and moved to the United States in 1934. So that's 19 years old. Now, during World War II, he was placed under house arrest as a potentially a spy, basically a I forget what the term was used. It was the way the Japanese were considered potentially spies. But even though he was under house arrest, he obtained, well, prior to that, he obtained his bachelor's degree at in MIT in 1937, and he was getting his master's at Harvard. And even though he was, quote, under house arrest, he was allowed to continue to work on his master's work at Harvard. And he received his master's at Harvard in 1934. They were both done in physics. Now, Feistel continued to continued to work on getting his US citizenship and obtained it on January 1944. The following day that he got his citizenship, obviously his house arrest was removed, and he was immediately granted a security clearance and began working for the US Air Force Cambridge Research Center on identification friend and foe devices until the 1950s. IFF devices are used not only in the naval ships, but also in airplanes. So they are the way in which you can find out whether another approaching object in radar is a friend or a foe. And he worked on that at the Air Force Research Center until the 1950s. He was then moved over to MIT's Lincoln Laboratory, which was under World War II, the development of radar. And then he moved to the MITRE Corporation and finally went to IBM. Now, there were all these questions in corporations about whether or not you could patent all of these mathematical ideas. So he just received an award at IBM for his cryptographic work. When I was working at Westinghouse R&D, the same thing happened for me because patenting was considered, if you were using mathematics, it was probably you wouldn't be able to get a patent. So they would just make everything a secret and give you a check. Anyway, his research at IBM led to the development of the Lucifer system, and then later in the 1970s to the data encryption standard, DES. And the structure used in DES, usually called a Feistel network, is commonly used in many block ciphers. This is, if you have keys, block ciphers are the kinds of things we were talking about just a minute ago. And Feistel was one of the earliest non-government researchers to study the design and theory of block ciphers. He married Leona Gage in 1945 and had a daughter, Peggy. Whoops. Okay, a block cipher is a deterministic algorithm operating on a fixed length group of bits called blocks. Uses an unvarying transformation. It uses a symmetric set of ciphers. That is, the key is the same on both sides, both in the encryption and decryption. And it's the elementary components and the designs of many protocols, and is usually used to implement the encryption of large amounts of data. It's part of the RSA system. So in a Feistel cipher, gotta get my language out, The block of plain text is encrypted to split into two equal-sized halves. So initially they used to be like 256 bits, and later they were to 1024, and now they're usually 9,000 plus whatever to the whatever is, and sometimes as much as 2 or 3 times that much in terms of the size of the number of bits that are used. So a round function, now again, you're using in a finite field. We talked about finite fields last time. And you apply 1/2 using a subkey. This would be part of the one pad key that would be sent back and forth in the RSA method. And so you create a coded version. You encode the other half, then you XOR the two halves. I'm sorry, you XOR the other half, and then the two halves are then swapped. Okay, so it is a secure block cipher suitable only for encryption of single blocks of data at a time using a fixed key. So the method in which it is used is the way I talked about before, using the key being sent back and forth using the RSA method. There are other types of cryptographic protocols. One is universal hash functions. A universal hashing refers to selecting a hash function, which I'll talk about in the next slide, at random from a family of hash functions with a particular mathematical property that guarantees a low number of collisions in the expectations. And I'll talk about collisions in the next slide. So all of this is used as one of the other protocols. And then what somebody started talking about, pseudo-random number generators. They can also be used as part of that. So a hash function. A hash function is a mapping. We've talked about morphisms. It's a morphism. It maps the data of arbitrary sizes to fixed sized values. So the values returned by a hash function are called hash values, hash codes, digests, or simply hashes. Now, the values are used to index in a fixed size table called a hash table. So figure 5 here, you've got keys, John Smith, Lisa Smith, Sam D, and Sandra D. And you've got hashes that are 0 to 15. And so Lisa Smith goes to 01, Sandra D goes to 4, John Smith goes to 2, and Sandra D goes to 2. So the hash function causes you to find any one of these particular strings of text, and it maps it into an integer between 0, and 15.
Did you see my hand?
Yep.
Okay, we lost you at
Okay, you're now losing.
I think we lost you at John Smith goes to.
Okay, so John Smith goes to 2, Sandra D also goes to 2. That's called a collision. Now, in a hash table, if there are multiple results, you have to say, oh, this has 2 possible results. One is John Smith and the other is Sandra D. So you have extra information that has to be added to the hashes in order to be able to invert the hashes back to the keys. So that's why you want to minimize the number of collisions. So the hash function, the property that we were talking about in a hash function that you have to use is to minimize the number of collisions using that hash function. Okay. So a hash function to index a hash table is called hashing or scatter storage addressing. So a Feistel cipher uses a symmetric key algorithm that uses the same cryptographic keys for both encryption of plain text and decryption of ciphertext. Again, this is the symmetric key idea. Keys may be identical or may be a simple transformation and go between the 2 keys. Keys in practice represent shared secret information between 2 different parties. That's the reason, and the way in which they're transmitted is using the RSA portion. The keys are used in the RSA. So that means so that both parties can get access to the secret key. So there is no, you have to keep sending the key back and forth between the sender and receiver. But once you have those keys, they're much easier to create and decode the block bits. So the public key encryption system, known as the asymmetric key encryption, which is what Steve was talking about, is an asymmetric key encryption system. And I'll discuss that next. Any questions? Okay, RSA stands for Ron Rivest, Adi Shamir, and Leonard Edelman of MIT. And they created the most popular and usable version of the system, christened RSA after their initials. And what they all discovered came to be known as public key cryptography, and just completely was a revolution in cryptographic circles. It completely solved the problem of key distribution. It allows phones, web browsers, email systems, anybody to communicate privately over public networks. That privacy is not absolute privacy. Shannon's information theoretic privacy of a one-time pad. Instead, the privacy of public key cryptography, the RSA system, comes from the trapdoor function. The fact that it's very, very hard to decode, to find the factors of a very large number of, which is the multiplication of two prime numbers. So the essential idea of public key cryptography is to separate the process of encryption and decryption. That's one of the reasons it's called asymmetric. The mathematical process of encryption, turning plain text into ciphertext, uses a number that is the product of two prime numbers. That product is the encryption key. However, the process of decryption requires the prime number factors themselves, and they make up the decryption key. So I've actually said a lot of this already. So the encryption key is public and distinct from the decryption key, which is kept secret or private. This is the asymmetry and is based on the practical difficulty of factoring products of two large prime numbers, the factoring problem. It turns out that Clifford Cox, an English mathematician working for the British Intelligence Agency, the Government Communications Headquarters, GCHQ, had developed an equivalent system in 1973, but it wasn't known at the time.
Bob, we lost you at, it turns out, Clifford.
Okay, turns out that Clifford Cox, an English mathematician working for the British Intelligence Agency, Government Communications Headquarters, GCHQ, had developed an equivalent system in 1973, but nobody knew about it because it wasn't declassified until 1997. So it was the early 70s and then the later 70s that created the systems that are actually in use.
I have a question.
Yeah.
And perhaps you're going to cover this. I don't know, maybe it's not here. I understand what you're saying. What I still don't understand is how the other end that needs to decode gets the, you say that the result of the prime numbers, the multiplication of the prime numbers is public with this system. What is not public, what is kept private, are the prime numbers needed to make that result. So that would be the same for anybody looking at it, you know, Russia. But if you want Britain to know about it, how do you get them the prime numbers?
Well, there's two parts. One is a database that has all the public ones. So in PGP, which is known as pretty good privacy, it's a system that's developed using oh, who's the guy? Oh, I've met him a couple of times. Oh,
It's Zimmerman.
yes, yes.
The reason why I know that is because I actually interviewed him for the physics department, for entering our physics department, and I had him in a number of classes that I taught.
Uh-huh.
Philip
Okay.
Zimmerman.
Yes. Anyway, he created PGP, and you can, it is a free system, and you can create your public key by choosing any kind of a large set of factors for your key. That's the public key. But there has to be another secret key in another database. And so anybody can use the public key to encrypt a message. But the people on the other side have to be able to access the secret key. And when did it
It has to be another. There has to be another is where we lost you.
okay, there has to be another secret database of keys, the private keys, that you have to have access to that. And so the PGP system, the code inside it knows what the private keys are, and only the code accessing PGP can use the private key to decrypt a message that you send.
I understand this. How do you get this private database? You fly it on an airplane or something?
No, it is created in the database itself. It is, nobody knows what it is. The system creates it and puts it in a database. So the PGP group creates these decryption private numbers in a database, and you create your encryption, but in order to decrypt it, you need to know the private part, and the PGP the code in PGP accesses that. It is the only equipment that can access that database.
I guess I understand. Perhaps I'm not understanding. The United States wants to send a message, and a database is created to use to decrypt or the code, or decode the message. I'm using the wrong words. How does England, who's receiving the message, get the database?
Well, in point of actual way in which it would happen is that a encrypted version of the database using perhaps the RSA method would be sent over the Ethernet to Britain, who would put it on their servers, and their servers would decrypt it, and they then have a copy of all of the decrypting keys. So you have everybody who is able to decrypt, and that is the key part. That's the asymmetric part. Only people who are allowed to decrypt can access the decryption keys. I'm waiting to see if you understood.
That's where we lost you.
Where was it?
Only people who are allowed to decrypt can access.
Yeah, only those people who can have the permission to the decrypted database can have access to it. So if you are sending a message, you have to know the identity of the person sending the message. And unless it is part of the whole system, unless they're known to be okay to receive that message and decrypt it, only those people on the decrypting side can access the database of private keys. Does that make sense?
I don't know that it's addressing what I'm trying to ask. There has to be
a table of usable people. You have to have a database of everybody who can use the system.
Yes.
So in PGP, you create your public key. That goes into a database. Only people who have their public key can be sending messages to be decrypted. So that database is open and anybody can look at it.
Right.
But the decryption keys are not known to anybody except the code that actually does the decoding. And you have to know both codes, both sides, in order to do the decoding. So you send a message that's encrypted. The receiver knows that you're in the list of allowable people to send messages encoded. That's in the original public data. So now they take the encrypted code, pick the appropriate decoding code from the private database, decrypt the message, and they have it.
I understand all of that. I just didn't understand how both sides of this transaction both started out in the beginning getting that private database.
Well, it's created by the system. Okay, so RSA is a company. They create the private databases. They encrypt them. They move them around in places so that nobody will know what the databases are. They make copies of them at the places where the code can be decoded using the same software that they use. They can, because of the way they're doing it, they can decode all of those databases in other places and make copies of it.
Okay.
Okay, so RSA uses it's a actual company that does it, and they have all of this equipment worked out. In PGP, it's done free, but it's essentially the same system that RSA uses. And it does the same thing. It encrypts their private key databases, move them around to different places and make copies of the databases in various servers and decrypts them there, and usually actually you only decrypt them when you need to decrypt the key, the message being sent. So the private keys are kept encrypted, you decrypt them, use the decrypted one to decrypt the encrypted message sent, and you have the decrypted message sent. It's a logistics problem. Anyway, like I said, the RSA is a relatively slow algorithm, and because of this, it's not usually used to directly encrypt the user data. The keys of a symmetric key cryptography system is used. Only the keys use the RSA encryption and decryption. And the same thing is true in the PGP system. Okay. So the original idea of asymmetric public,
The same thing is true.
okay. The same thing is true of the the same thing is true. Can you hear me?
Yes.
Okay. The same thing is true of the PGP system as the RSA system. They're, you know, one was done for free for everybody, and the RSA is a company that makes money off of it. So, but the idea of an asymmetric public-private key cryptosystem was actually published first by Whitfield Diffie and Martin Hellman. They published this concept in 1976. They introduced digital signatures and attempted to apply number theory. Their formulation used a shared secret key created from exponentiation of some number modulo a prime number. However, they didn't understand how to actually use one-way functions or trap doors. And the probable reason why they weren't able to understand about that was the difficulty of understanding the difficulty of factoring, which was not well studied at the time. Ron Rivest, Adi Shamir, and Leonard Adelman at MIT made several attempts over the course of a year to create a one-way function that was hard to invert. Now, as computer scientists, they proposed many possible functions. The Edelman was a mathematician, and so Rivest and Shamir would come up and say, I think this is a good one. And Edelman would take a look at their system and say, no, it's got this weakness or that weakness. So they tried many approaches, knapsack-based functions. Knapsack are basically large linear programming problems that you need to have a very complex linear program in order to be able to figure out how to maximize the amount of stuff you can put in the knapsack. That's what the knapsack problem is. They tried permutation, polynomials. They tried a lot of different things. In April 1977, they spent Passover at the house of a student and drank a lot of Manischewitz before returning to their homes around midnight. Rivest was unable to sleep. he lay on a couch with a math textbook. He started thinking about one-way functions, and by the rest of the night, he formalized all of his ideas. And by daybreak, he already had most of the paper ready. The algorithm, now known as RSA, the initials of their surnames, in the same order as their paper that was published within a month. Clifford Cox, as I talked about, the English mathematician working for the GCHQ, described an equivalent system in 1973. However, the relatively expensive computers needed to implement it at the time were very hard to work with, and it was considered a curiosity, not as a actual usable system, and it was never deployed in Britain. His discovery was not revealed until it was declassified in His discovery was not revealed until 1997 when it's declassified. Now, KID RSA is a simplified public key cipher system published in 1997. And it's designed for educational purposes. And some people feel that learning KID RSA gives insight into RSA, other public key ciphers, analogous to simplified VES. It was, at the time we got to the beginning of the lecture, that I was working on KID RSA, and I don't have the code. I don't have the work for this in the current PDF that we're looking at. So we'll start next week with KID RSA in order to show how RSA actually works. And I apologize, I just didn't have the time this week because I spent most of my time uploading to YouTube for all of the lectures that we have done previously, and going through and cleaning some of the Okay, now you can hear me?
Yes.
Okay, so next week we'll start with KID RSA. I spent most of the week this week cleaning up some of the lectures and putting them together into a place that you could download them in the spreadsheet that I sent you, as well as putting the lectures we had into YouTube. And I sent another spreadsheet of all of those links for those YouTube ones. So I didn't have enough time to finish KID RSA this week, and we'll start it next week. Oh, oops. So this summary is not quite right because I had been expected to finish it before I got to this, but we're not going to do that. So last week I described Hamming codes, and in particular the famous Hamming 7.4 correcting code with examples. This week I provided a short description of encryption, a short background, the work on Horst Feistel, especially DES in the 1970s, which is actually still used most of the time today. It's part of the advanced encryption system algorithm approved by the NIST in 2001. As I said, originally it was 128 bits. I thought it was 256, 128-bit blocks. But now the codes are usually, like I say, thousands of bits in a block. And then we started talking about the RSA, public key crypto system. Next week, I'll start with KID RSA and then move on to Hamilton flows. And if time permits, begin on idospace. So, questions?
Thank you. I do have one very quick question. That is, how much stuff that's flowing back and forth across the internet is encrypted like this?
Oh, almost all of it.
Okay, so there's pretty much what we see. Even the video. I mean, everything. You're looking at the challenges we've had just today of bandwidth and keeping the tube flowing. So this is all encrypted information.
Yes, all of this stuff is encrypted back and forth. Any other questions?
I have a few comments, just a few
Okay.
things. First of all, there's this really neat television program. It's in reruns now. They only did 1 season or 2 seasons, called The Bletchley Circle. Anybody ever? And that has to do with decryption during World War II. And I heard them talking about pads. And one of them had to do with somebody stole some pads or something. And I never understood what that meant. And now I do. And it's really interesting.
Yeah, no, I haven't watched those videos, but I have read the book about Bletchley Circle. So yeah, that is exactly what they're talking about, is the one pad key. And if you have, I mean, that's one of the things I didn't talk about, is that one of the decryption methods is called rubber hose. And if you have somebody, when you have actual physical pads, you have to move them from place A to place B. And somebody, a courier, somebody has to actually physically move them from location A to location B. And, if somebody's carrying that, an enemy could intercept the courier and, using violence, force them to give you the key, the pads that they have in their courier bag. So yeah, that's exactly what they're talking about.
It's fascinating, and this helped me understand that more. The second thing I wanted to mention was my father, his career was at North American Aviation, as it was originally called. It became North American Rockwell, and he was not an engineer, but his final job was to hand out, evaluate and hand out awards, just as you were talking about, to employees who had submitted either findings or suggestions or something that made things easier, faster. In other words, it saved the company money, in effect. So that is what he did.
Yeah. No, in my case, I had actually worked through designing, using spline techniques to design the blades of turbines. And I submitted that patent, and they decided that it was going to be a company secret, and not give it to the patent office because they didn't think that it would be allowed because it was primarily mathematics. And so instead it was, made a secret, and I was given a check. So that was the way, my particular way did it, and the same way that IBM did it for Horst Feistel. Again, his material was primarily mathematics, and at the time, it was thought almost impossible to get any mathematical methods patented. So they were always just made a company secret.
But even if something could be patented, the person who figured it out or thought it up would not hold the patent. It would be the company, right?
Right, right.
When you worked for a company, they were the owners of all of your ideas.
Right, that was true. And they would give you a fee for that as well. But in that case, they would hold the patent and actually be able to use it. In both Horst's method and mine, the stuff was company secrets.
Mm-hmm.
Any other questions? All right, I'm going to stop the recording. Stop.